Welcome back, students. In this video segment, we will cover two extremely important sections in this course. The first is section 16.5. It's called Curl and Divergence. And then the absolute most important section of the two, 16.9, called the Divergence Theorem. The Divergence Theorem is a theorem that holds a lot of physics together, a tremendous amount of physics together. Okay, in electromagnetism, it's often referred to as Gauss's theorem. Okay, so let's get started. In order to look at the divergence theorem, we're going to need the concepts of surface integrals and flux from our previous section. So what we'll do is we'll just sort of do a little recap or review of some of the important topics from the previous section. So recall. We have something called the orientation of a surface. If a surface is closed, then the positive direction or the positive orientation of the surface is outward. Okay, if a surface is not closed, then we have to specify the orientation of the surface. Okay. And to specify the orientation of a surface, we specify a unit normal vector for the surface. Okay, and there was a whole part of the discussion that went along with that. Also, if we have a vector field F that's defined on an oriented surface, so I've pictured sort of an umbrella-shaped surface off to the left there. If we have F defined on an oriented surface, then we have something called the flux of F across S, and that's given by the surface integral of F dot n ds, a very, very important quantity. In the previous section, we looked at an example where the vector field F was the velocity of a fluid. In particular, it was orange juice coming out of an exploded orange. An exploded orange that somehow retained its shape with the help of a steel mesh that was placed around it. So if V is the velocity of the fluid, of the orange juice in particular, then the flux of V across S, across the surface of the orange, is the rate at which fluid crosses the surface, or the rate at which orange juice leaves the orange from the point of view of, and I think I use the idea of a little person standing on the orange, measuring with some sort of meter, an orange juice meter, the rate at which orange juice was crossing the surface of the orange. And then we had a little bit of notation. It's very common to use the notation for the flux integral, or F dot n ds, as F dot ds, where ds is shorthand for n, the unit normal times surface area of a differential element of surface area ds. So the n ds is referred to as the differential of the vector s. Okay, it's similar to when we talked about line integrals, when the work integral f dot t ds can be written shorthand as f dot dr. Okay, so let's start with an example. This example is still material from the previous section, but I'm going to build on this particular example. So I want to look at a specific example of computation of a flux integral, and we'll expand on this with when we get to the divergence theorem. So evaluate the flux of F across a surface S, that is the surface integral of F dot n ds, where F is the vector field represented by the vector whose components are y, x, and z. And S is the boundary of the solid region E, and I pictured it down below for us, enclosed by the paraboloid z equals 1 minus x squared minus y squared, and z equals 0. So this is where we'll begin our work for tonight, or today. Tonight or today, depending on when you're watching this. Okay, so what we're going to do is we're going to break this surface S into two pieces. We're going to say that the region S is broken down into S the top, S top, which is the paraboloid, and union S on the bottom. And on the bottom, we have z equals 0. So the flat z equals 0 is on the bottom. Okay. Well, to compute the integral of f dot n ds, we're going to need a unit normal. So let's compute the surface integral or the flux across the top first. And by the way, we're going to be using the idea that the surface integral across S is equal to the surface integral, just for shorthand, S top plus the surface integral of S over the bottom. So let's compute the surface integral, the portion of the surface integral over the top of the surface. So I'm going to need a normal. So we're going to assume the positive orientation. So we're going to be computing the flux of this vector field across the surface, assuming a positive orientation. So I'm going to need an outward normal. So I'm going to picture that. I'm going to call that n sub 1, and I'll draw it in red. So here's n sub 1. It's pretty clear that n sub 1 is the upward normal for this paraboloid, the upward normal. Remember, the upward normal is the unit vector that has 1 in the z component before dividing by the length to make it a unit vector. Okay, so if you've forgotten that, n sub 1, oops, unit vector n. Let me do this. And unit vector sub 1 is the upward unit normal, and it is minus gx minus gy 1 divided by the length of that same vector, divided by the length of minus gx minus gy and 1 from our previous section. Okay, where g is the paraboloid. G of xy is 1 minus x squared minus y squared. So we have, let's go ahead and do this. Let's find n1. We have g of xy is 1 minus x squared minus y squared. So g sub x is negative 2x, and g sub y is negative 2y. So that gives us our normal for the top portion of our surface, S top, S sub top, as minus 2x, comma, the vector whose components are minus 2x, minus 2y, and 1. The 1 is an indication, is the indicator that our normal is oriented upward. And then we divide by the length of that same vector. So it's over the square root of, and I'll do this in reverse order, 1 squared, and then plus 2x squared plus 2y squared, negative 2x squared plus 2y squared. So when I square 2x and negative 2x and square negative 2y, I'll have 4 as a common factor. I hope this isn't too many steps. Okay, so I'll have 4x squared plus 4y squared plus 1. I can factor out the 4 from the x squared plus y squared. Okay, all right, so let's compute the surface integral, or the flux, surface integral or flux, over the top, over S sub top of f dot n ds. Okay, so let's go ahead and replace or substitute these quantities. So this is S top. The F is y, x, z. So at the point x, y, z, the vector field is the vector whose components are y, x, and z. Okay, so you could interpret this as the velocity vector of a fluid at the point x, y, z if you want to, but it's not necessary. It could be electric field or other quantities. Okay, so there's f dot n, so negative 2x, negative 2y, 1 over the square root of 1 plus 4 times x squared plus y squared. Okay, and that's ds. All right, let's compute that dot product. So this is the flux integral over the top, or the surface integral over the top surface. Computing the dot product. Let's see. You know what? I think I have a sign problem with our. I think I have, and you probably saw this, but there's a sign problem in our normal. Notice the formula for the normal up in the right is minus gx minus gy1, and gx is minus 2x, so minus gx is plus. Someone might even have left a comment already in the video section before I had a chance to correct this. You don't have to erase your comment. You could leave it there. Well, you probably should erase it because it's corrected here, but whatever. Okay. So now let's compute this dot product. So we have y times 2x is 2xy. We have x times 2y, which is 2xy. And we have z times 1 is z over the square root of 1 plus 4 times x squared plus y squared ds. Okay, so we've turned this flux integral into a surface integral of a scalar function. Okay, now let's evaluate this surface integral. How do you evaluate the surface integral? You stuff the formula for the surface into the function and turn it into a double integral over the projection of the region, of this region, in this case, into the xy plane. So this gets turned into the double integral over d in the xy plane of, well, we have, I'll just leave it as 2xy plus 2xy for now. 2xy plus 2xy, so you can see where everything came from, plus z. Well, the formula for the surface is z equals 1 minus x squared minus y squared over the square root of 1 plus 4 times x squared plus y squared. And ds is the differential element of surface area. And what I think I'll do is off to the side over here, I'll compute ds. It's a little sloppy, I guess, but I think it might be convenient. So ds, remember, is the square root of 1 plus gx squared plus gy squared. That should look familiar. That's part of the normal vector. It's in the denominator of the normal vector. So you might be thinking, well, that's going to cancel with the denominator for the normal vector. Yes, it will, and it will every time. But I want you to show this. I want you to show this on your final and your homework. And I'm going to be real explicit about this right now. I want you to show the computation of ds. I don't want you to use a formula that your author gives you. And let's see, I want to give you the place where your author goes right to a formula. I don't want you to do that. I want you to compute this surface integrals the way, or these flux integrals the way I am directly. Do not use page 1170 in your text, formula number 10. Okay, I don't want you to do that. I don't want you to do that. I want you to compute these surface integrals directly this way. Okay, and I'm going to write that explicitly here. Do not use formula 10 from the textbook on page 1170, of the text. Okay. It's no big deal. It's not something you need to obsess too much over. Just evaluate the integrals the way I'm showing you here. Okay, it emphasizes knowledge of what you're actually doing and stuff, and not just memorizing formulas. Okay, so let's compute ds. This is the square root of 1 plus g sub x is negative 2x squared plus negative 2y squared. We're going to get that nice cancellation happening. dA, or the square root of 1 plus 4 times x squared plus y squared dA. And that's pretty cool. That's pretty cool. So I'm gonna put ds in now. So ds into our, remember when we convert the surface integral into a double integral, we write the formula for the differential element of surface area, which in our case is, oops, go back to black. Square root of 1 plus 4 times x squared plus y squared dA. Okay, so we're gonna get some simplification going on here. So this is the double integral over d in the xy plane of, let's see, how do I want to write this? That's fine. This is 4xy. Let's see, plus 1 minus x squared minus y squared dA. And this is a regular old rectangular, like it's a regular old double integral from our past. And I said rectangular, but I think we're going to go ahead and go to polar here. The suggestion for polar is given to us in this integrand. It has x squared plus y squared in it, and also our region, the region in the xy plane over which we're integrating, is a circle. It's a unit circle. Okay, so let's do this. Let's evaluate this as an iterated integral, and let's go directly to polar. Well, x equals r cosine theta. I'm gonna rewrite 4xy in polar form. X equals r cosine theta and y equals r sine theta. So 4xy is 4r squared sine theta cosine theta plus 1, and then minus x squared plus y squared is minus r squared. And dA, of course, is r d theta. And the region D over which we're integrating happens to be, the bottom of our surface, the bottom part of our surface. Okay, which is the unit circle centered at the origin. How do I know that? How I know that is that the formula for the surface is z equals 1 minus x squared minus y squared. And on D, z equals 0. So 0 equals 1 minus x squared minus y squared, or x squared plus y squared equals 1. So that's pretty cool. Okay. So r goes from 0 to 1, and theta goes from 0 to 2 pi to sweep out the entire circle. And then we'd evaluate this. I'm not gonna do the evaluation on camera. It's a little bit of work. It's not a lot of difficult integration, but this equals pi over 2 after some integration. It's not too tough, and I think I can leave that off. I'd like to know, and this is really a big question here. I'd like to know how I can cut down on some of this work. How can we cut down on some of this work? How can we cut down on some of this work? And unless you're familiar with the divergence theorem, then the answer is I don't know, which is just fine. Okay, so this is coming up soon. Coming soon. That's really the big reason why I've come up with this particular example. Okay. Okay, so let's see here. In order to discuss something called, or not something called, the big thing for our lecture tonight, which is the divergence theorem, we need to talk about a quantity called the divergence of a vector field. We need to talk about a quantity called the divergence of a vector field. Vector field. Let's say, we can call it F or V. Let's call it V. Okay, or div of V, something brand new for us. Now we're using a term that we used intensely in Calculus 2. We used the term divergence to talk about sequences and series diverging. That we're using a divergence in a very, very different sense here. So there's no connection between divergence or the divergence theorem and the divergence of series. Okay, it's simply that we're using the same word to represent two different things. Okay, so let's talk about what we mean by the divergence of a vector field V. To make this this discussion intuitive, I'm going to assume that V represents the velocity of a fluid. Orange juice, if you'd like, because we are going to return to the exploding orange problem eventually. But I want to interpret the vector field as velocity. It doesn't need to be velocity in general in physics to have the concept of divergence, but it really helps for us to do this intuitively. So let's let the vector V equal V of x, y, z. So V is a vector that depends on the location of a point x, y, z. So V is a vector associated with a point. So let's let V be the velocity of a fluid at the point x, y, z. Okay, so it tells us the direction in which a fluid is flowing, and the length of the vector tells us how fast the fluid is flowing. Now here's an intuitive definition of the divergence. The divergence of V is the rate. It's going to sound a little funny here, but it's very common. These kinds of quantities are very common in higher physics. It's the rate at which fluid leaves or enters. You can think about leaving, though, for now. Leaves or enters a point. Now, already we have something that's very difficult to conceptualize because a point has no dimensions, yet fluid does. So we can think about a point as being an infinitely small box. So think about the divergence of V as the rate at which fluid leaves or enters, but we'll think leaves a point or a really tiny box that contains the point x, y, z. And here's where it gets a little strange, if it's not strange already. Per unit volume, and you can think about it as the unit volume as enclosing that point. I'm gonna try to make this more clear in a second. Okay, so it's the rate at which, now it's a quantity that's defined at a point. You can think about it as the rate at which fluid leaves a point, or a really small box that surrounds that point, per unit volume that encloses that point. Now I'm gonna give you an example to kind of conceptualize this quantity. Okay, so the units, first of all, the units of the divergence, the units of, so let's say possible units of the divergence of a vector field V are, well, let's see, the rate at which fluid leaves in cubic centimeters or cubic meters or cubic feet. So cubic centimeters per second, that's the rate at which fluid leaves a point per unit volume surrounding the point. Okay, or in cubic centimeters cancel per second. The square indicates there's nothing there. Or very commonly in physics we write seconds to the -1. So the units of divergence are per time. Okay. Now I know it seems a little strange, but here's my attempt at making this really understandable. And your author doesn't do this. Your author he'll end the discussion at the rate at which quantity leaves a point per unit volume. I'm not even sure if he goes that far. Okay, so here suppose for example, suppose that a small box of volume 10 to the -3 cubic centimeters contains the point 1, 2, 3. Okay, so suppose a small box of volume, and we'll say that we're going to give the volume a quantity dV, is 10 to the -3 cubic centimeters. It's pretty tiny. It's not that tiny, but that's tiny enough. And that box encloses the point 1, 2, 3. So here's the red point 1, 2, 3, and I have some box that encloses that point. So that point is inside the box. It doesn't look like it's inside the box, does it? I'll move that point. Hard to draw a point in a box. So there's a point inside of a really, really, really small box. The divergence might seem strange on its own. The divergence of V might seem strange on its own. But let's say, suppose, let's do this. Suppose the divergence of V at 1, 2, 3 is 3, or 3 cubic centimeters per second per unit volume, or 3 per second. Okay, so again, we're making the assumption that V is the velocity of a fluid, and at 1, 2, 3, the divergence of the velocity at 1, 2, 3 is 3 per second. So this now will give the quantity divergence some meaning. Then what is the divergence of V at 1, 2, 3 multiplied by dV? It will be 3 per second times 10 to the -3 cubic centimeters, or 3 times 10 to the -3 cubic centimeters per second. So when you take the divergence of the velocity vector at a point and multiply it by a small volume that surrounds that point, then what you get is the rate at which the fluid leaves that box. So the divergence alone doesn't give you the rate at which a fluid leaves a box. The divergence of a velocity vector gives you the rate at which fluid leaves a small box per unit volume times the volume. So if you multiply that divergence times the volume of a very small box, you get the rate and the net rate at which the fluid leaves that box. So this is the rate at which volume leaves the box of volume dV. Of course, that box has to include the point 1, 2, 3. Okay, the divergence of V is called the flux density. Similar to the concept of density that you learn in chemistry, density is mass per unit volume, mass over volume. Well, the divergence is flux density. Flux, remember, is a rate. So it's rate per volume, which gives you something called flux density. Okay. Your author does give a real nice and a very common, but also real nice piece of sort of intuitive information about the divergence. So if let's do this. If the divergence, and it is a scalar quantity, I think you see that, but just in case, divergence takes a vector quantity and turns it into a scalar. So if the divergence is greater than 0, you can think about it as if this is the point XYZ, that the divergence tells you that the fluid is exiting, then the fluid is leaving or exiting through a small hole, through a small hole at the point XYZ. So you can think about as the fluid is leaving or diverging, if you will, no pun intended, diverging from that point. Okay, the point XYZ is called a source. Okay, so liquid is coming out of that little hole. So if the divergence is positive, and you have that point called a source. If the divergence of your velocity vector at a point is less than 0, then fluid enters. Through an infinitely small, or just a small hole at the point XYZ. Okay, so if this is the point XYZ, you can think about it as the fluid is going into that hole. So what do we call that hole, that little hole, when fluid is escaping through that hole? That point is called a sink, like our kitchen sink or bathroom sink. XYZ is called a sink. You have something called sources and sinks. So if the divergence is less than 0, the tendency of the fluid is to enter that small hole. Okay. All right. So let's return to the exploding orange problem. This is a very, very, very important problem for us. And again, remember, this is my problem. I invented the problem for a talk I gave to the math department to explain the divergence theorem. So you won't find this, I don't think you'll find this anywhere else. Okay, so back to the exploding orange problem. Previously, we imagined a little person was standing on the outside of the orange. Okay, so the person has no possible view of the inside of what's going on inside the orange, except for maybe getting information about what's going on inside by noting about what's passing through the surface. So the little person standing on the orange, all that person can do is observe what's coming across the surface, has no idea of what's going on inside the orange. Okay, maybe heard the loud explosion, but I can't make any assumptions. Okay, we figured out that the rate at which orange juice leaves the surface is the surface integral of v dot nds, or the flux of v across s. This is computed by observing what's going on with the vector field only along the surface. Okay, now we're going to change our point of view. Our point of view now is going to be inside the orange. So here's our orange again, and we're going to put our new person inside. We'll put the person dressed in a dress. Just sort of to indicate that we're putting a new person. I'm putting the person dotted too to indicate that this person's inside. Point of view inside the orange. Okay, that person cannot see what's going on outside the orange. From that person's point of view, that person can only observe orange juice passing from the inside to the outside without seeing what's going on outside. The only thing that person can see is orange juice leaving the interior. Okay, so let's divide. Imagine that person is dividing. Divide the interior of the orange into infinitely many, infinitely small boxes. Divide the interior of the orange into infinitely many, infinitely small boxes of orange juice. Infinitely many boxes of volume, since they're going to be really, really small, dV. Okay, so inside that orange, here's a typical box. This is inside the orange, and this person, we'll call her she. This person can observe what's going on with the orange juice as it leaves that box, just that one little box. And she can go to the next box, the next box, the next box, and so forth. So, using our previous example, our only example with divergence, the rate at which orange juice leaves that one little box, leaves the tiny box, is the divergence of the velocity times the box, the volume of the box, dV. Okay, remember the divergence gives you flux density. It gives you rate per unit volume. Okay, that's divergence. And dV is volume. So the rate at which orange juice leaves that one little tiny box is divergence of V dV. So what if she wants to compute the rate at which orange juice leaves what if she wants to compute the rate at which orange juice leaves the entire interior Well, she can take the rate at which orange juice leaves that one box and add it to the rate at which orange juice leaves the box right next to it, and the rate at which orange juice leaves the box right next to it. She can add up all those rates as she moves along the interior of the box of the orange. Okay, so how is she going to sum up those rates? She's going to take the triple integral of the divergence of V dV as integrating throughout the interior of the orange. So integrating over the interior of the orange. So when she sums up all those rates, that should give you the net rate at which orange juice leaves the interior. So the net rate, or total rate, net rate at which orange juice leaves the interior. Of the orange. Okay. So here's the divergence theorem. The divergence theorem is based on an obvious fact. Obvious fact. Now, assume the person on the outside can now call, using their cell phone, the person on the inside. The person on the outside is going to tell the person on the inside the rate at which orange juice is leaving the surface. The person on the inside is going to completely agree with that person. Both points of view should give the same rate. The rate at which the orange juice leaves the surface should be the rate at which orange juice is leaving the interior. Does that kind of make sense? The obvious fact is the point of view, let's see, both points of view. So let's do this. Both points of view should give the same result. That is that the triple integral of the divergence of V dV over the interior, let's say E is the interior, should equal the surface integral, the flux of V dot N ds over the surface. Okay, this is called the divergence theorem. This is the divergence theorem. It says you can get information about what's going on the inside of a surface by computing a surface integral on the surface. You can compute what's going on the inside of a surface, inside of a solid, by computing a quantity on the outside, just on the surface, without ever looking on the inside. The left-hand side of this equation is a computation of what's going on inside the solid. The right-hand side, the perspective is purely on the surface. Why is that important? And it's not important so much for observing rates at which orange juice comes out of exploding oranges, but think about how that might relate to be important for getting information about what's going on inside our planet. We can't go to the center of our planet. We can barely go to scratch the surface of our planet physically. What's the radius of our Earth? Isn't it like 3,900 miles or something like that. We can't go very deep into our planet. However, we have a pretty good idea, we think, of what's going on inside our planet, deep into our planet, at the core of our planet. So we can get information about what's going on inside our planet by computing a surface integral. Okay, how do we know? Well, we don't know because we can't go down there. How do we surmise that the core of our planet is a molten ball of iron twirling around? We use the divergence theorem by computing or observing what's coming out of the surface. So the divergence theorem has massive ramifications, huge ramifications for physics. Okay. So let's return back to our initial problem. Okay, so let's, not our initial, I guess it was our initial problem. Let's return, example, let's return to the integral of f dot n ds for our previous example. I'm going to stop the video and bring it back for us. I'll be back in just a couple seconds. Okay, so here's our previous problem. It was to evaluate the integral of f dot n ds, where f was y, x, z component-wise, and s was the boundary of the solid region enclosed by the paraboloid, and the plane z equals 0. And we ended up with the integral over the top was pi over 2. We didn't finish. We didn't integrate over the bottom. So let's finish the problem, and then we'll use the divergence theorem to maybe make things a little simpler. So now let's figure out the flux through the bottom of the surface. So we're going to need this is very easy. We're going to need a downward normal. So let me redraw. So N2, well, what's N2? N2, remember the bottom of our surface is the xy plane, a disk in the xy plane. So N2 is just negative k. Okay, so continuing the long way, the direct computation of this flux integral, S bottom, it ends pretty quick after this, is of f dot n ds is the integral of y, x, z, f dot n 0, 0, negative 1 ds over the bottom of this thing, over the disk. Now, if you perform that dot product, you get y times 0 is 0, x times 0 is 0, and z times negative 1 is negative z ds. Now, how do you evaluate a surface integral? You stuff the formula for the surface into the function and then integrate over the surface, that portion of the surface. Okay, well, on the bottom, what's z equal to? On the bottom surface, z equals 0. So this one's a quick ending here. So this is over the bottom of 0 ds, which is 0. So the net result is that the flux of the vector field over the entire surface, S, is pi over 2 plus 0, which is pi over 2. Okay, now I'd like to cut this work down. I'd like to redo this from the point of view of the inside. I would like to compute this flux the flux of the vector field over the surface by using the divergence theorem. So let's do that. So now by the divergence theorem, now let's use the divergence theorem. Now let's use the divergence theorem. Okay. So the F is y, x, z. Okay. The divergence of F is what's missing. We don't have a formula for the divergence. What is the divergence of F? Well, here's the big formula for divergence. Formula for the divergence of a vector field F. If F of xyz equals component-wise F1 of xyz, F2 of xyz, F3 of xyz, then the divergence of F it's a very simple formula. We're not going to derive it. The derivation is a little messy, and I've never seen it done in a textbook. It's a little messy, something that's not instructive. If you're a math major, you'll see the derivation. You probably have to memorize the derivation at some point. Oops, I'm putting the wrong derivatives here. But not for us. This is computational course in calculus. So the divergence is very simple. The divergence of a vector field is simply the partial derivative of the first component with respect to x plus the partial of the second component with respect to y plus the partial of the third component with respect to z. That's incredible. It's an incredibly simple formula. So the divergence of f in our example is the partial derivative of y with respect to x. Oops. I can't do the undo button here. Okay, is the partial derivative of y with respect to x, which is 0, plus the partial derivative of x with respect to y, which is 0, plus the partial with respect to z of z, which is 1. Okay, so the divergence of f is 1 for our particular integral. So the divergence theorem says that the surface integral, or the flux integral of f dot n ds over the surface is equal to, it's the same formula that I did for the orange with v replaced with the more general f, is the divergence of f dv over the interior. Okay, so the surface integral, the flux integral that we computed is now being replaced with the triple integral over the inside of that parabolic solid, if you will, of the divergence of f dv. The divergence in this case is 1 dv. So we're now just looking at the triple integral of 1 dv. In this case, since the divergence is 1, then we're just looking at the volume of the solid. Okay. Now remember, the solid is enclosed by the paraboloid above and z equals 0 on the bottom. Okay, so we can interpret this as a type one region very, very simply. So we can integrate from z equals 0 to the paraboloid, if we want to go to an iterated integral, go from 0 to the paraboloid, 1 minus x squared minus y squared dz, and then integrate doubly over the region in the xy plane. But the region in the xy plane is just the disk, x squared plus y squared equals 1, or is less than or equal to 1. So I can go all the way to polar now. I can go directly to polar to compute ultimately this triple integral. So 1, and replace dz dA with r dz dr d theta, where z goes from 0 to 1 minus r squared, x squared plus y squared is r squared. Now dr and d theta have to do with the disk x squared plus y squared equals 1, or is less than or equal to 1. So r goes from 0 to 1, theta goes from 0 to 2 pi to get all the way around. And this integral is very, very simple, extremely, extremely simple. So this is the integral from 0 to 2 pi, and then integral 0 to 1. Integral of r dz is rz, as z goes from 0 to 1 minus r squared. So I'm just going to evaluate this integral. It's so simple. Takes almost no time at all, but it's very different. The changing our point of view gives us very different computation. Okay. Integral from 0 to 1, r times 1 minus r squared dr d theta. Okay. So if we were to multiply, we're going to get integral 0 to 2 pi after integrating from 0 to 1, r minus r cubed dr d theta, super simple integral. Okay, so this integral 0 to 2 pi, 1/2 r squared minus 1/4 r to the 4th, using the fundamental theorem on the inside integral. So it's really just 1/2 minus 1/4, which is 1/4. From 0 to 2 pi, d theta from 0 to 2 pi, which is 1/4 of 2 pi, which is the same pi over 2 that we got by directly evaluating the flux integral. So we evaluate the flux integral, the integral over the surface, by now replacing that with an integral over the interior. Okay, and that's the whole idea with the divergence theorem. Get information about the inside by looking at the outside, or vice versa. Get information about the outside, evaluate a flux integral by evaluating a volume integral. So I'll end this video segment with a more formal statement of the divergence theorem. So the divergence theorem. So let's let E be a simple solid. And a simple solid is not mysterious. A simple solid means type E1, E2, or E3. Okay. And let S be the boundary of E. Okay, given with a positive or outward orientation. Let's say with positive outward orientation. Okay, let's say let F, we need a field, be a vector field. Okay, be a vector field. And the details that we don't have to obsess too much about are that they need to have continuous partial derivatives. Okay, so let's assume that f satisfies the conditions that are necessary for the divergence theorem, that the partial derivatives are continuous of the components. Okay, I'm not even going to write it out because for those conditions for our applications, this will always be true. Now, if you're a math major, the details are going to be super important when you get to those courses that expound on the divergence theorem and stuff. Okay, so the divergence theorem, then the divergence theorem says the flux of F over the surface, the information that you get by integrating over the surface, is the same thing as gathering this information, the triple integral of the divergence over the interior. Okay, that is, the flux over the surface of F over the surface is equal to the triple integral of the divergence of the vector field over the interior. Okay, extremely important theorem. Okay, and that ends this video segment. Okay, so I'm looking forward to talking with you all again very soon. Get started on the homework for these two sections as soon as possible. Okay, see you soon.